The next concept we are going to talk about is binary operations, and using binary operations and defining binary operations on sets, we will be able to define algebraic structures. And before we actually go into binary operations, I would like to touch upon the concept of abstract algebra. So why do we need algebraic structures? Why do we define them? Why do we use them? We generally have certain structures that have certain properties, like we have sets, we have defined operations on sets, or we have just numbers, right? Real numbers, rational numbers, integers, or complex numbers. We have certain operations on them. We have defined functions, and we know how to manipulate them. We know how to compute them, etc. And we have other structures. Let's say we have functions, and for instance, we can add or multiply them in certain ways. We can compose them. We have matrices. We have vectors, or we have other structures like graphs or topologies, and there are ways to manipulate them, operate on them, and define some mappings or functions among them. But we have what we call abstract algebra here, or mathematicians simply call this algebra. And here we have a certain level of abstraction. We will define algebraic structures where you have a set with certain types of elements, and you have one or multiple operations, binary operations, defined on the set. And based on these structures, we will define elementary algebraic structures that have certain properties that are generalizable. So we have a certain experience in, let's say, algebraic manipulations on numbers. That's easy enough. You can add two numbers, subtract them, multiply them, etc. You can arrange them in certain ways. We know how to apply distribution over, for instance, the distribution of multiplication over addition, etc. But we generalize these to abstract structures so that when we define a structure that fits the properties of, let's say, algebraic manipulations in numbers that have similar properties, then we can apply the results we already have from the structures we know to those new ones. So in a way, we are generalizing the setting in which we do arithmetic, addition, multiplication, and well, those are the basic two, but essentially subtraction and division are just inverse operations if they exist. And these will be meaningless in certain settings, for instance, in functions. What does it mean to, or on relations, what does it mean to multiply relations or polynomials? So you can define certain structures that apply general results that we derive on them to any circumstance that fits the setting. So to be able to do that, we start with the concept of a binary operation. A binary operation, and this is a symbol we use to denote a binary operation, but this is a very generic symbol. You can see like addition, cross product, a dot product, in a general sense multiplication, or you can see other symbols like triangle or a square to denote any operation. So this is in a sense a generic symbol that denotes we are doing something on these elements, or even sometimes we will drop the symbol altogether. And what's a binary operation? It's essentially a function. A binary operation on a set A is a function from the Cartesian product of A with itself to A. So essentially what this means is you have a function accepting ordered pairs from the Cartesian product of A with itself and produces another element again in A. Okay, that's what a binary operation is. Now, sometimes in the coming slides, we are going to refer to some operations as addition or multiplication, but these are not going to mean the familiar operations we know. The familiar operations we know are going to be special cases of these. But in a general sense, you can define the binary operation in any way you like, as long as it's closed. What does it mean? You take two elements in a certain order from this Cartesian product, and the result still must be in set A. That's what we mean by closed. So the result is still in the same set. Okay, so the result of the binary operation on two elements from set A is also again in the set A. Okay, this is closure property, and we are not going to be stating this. Okay, this operation is closed under this, etc., on the upcoming algebraic structure definitions. So when we say there is a binary operation on this set, you should automatically assume that it's closed. Okay, so again, let me emphasize this. The symbol, let's say plus or multiplication, or let's say a dot product, etc. It's just a symbol. It might represent any operation. It can also be the usual addition or multiplication, but it can mean something very different, a very generic operation. So do not be fooled by the name addition multiplication, nor the symbol addition or multiplication. Okay, what we are defining here is a very generic setting and an abstract setting. And as I say this, let me also remind you, we can define or we can denote operations in this way, or x plus y, or x times y, or maybe x dot y, or even xy without any symbol in between. This will mean I'm applying a binary operation to the ordered pair xy. Okay, some of these operations are not going to be commutative, so the order is important. That's why we are defining them on Cartesian products. Here are some examples. The usual ones we know: addition and multiplication on natural numbers, set of integers, set of rational numbers, real numbers, and complex numbers. Okay, these are all binary operations. Subtraction on integers, for instance, is an operation, yes, because it's closed. On the other hand, subtraction on set of natural numbers is not. Why? Because, for instance, if you would like to subtract 8 from 2, which are both natural numbers, the result, as we know, is -6, which is not a natural number. So this operation is not closed, which means it's actually not a binary operation. Exponentiation on natural numbers, for instance, take any natural number, you get 5 to the power 2, that is 25. It's still a natural number. It's closed, therefore it's a binary operation. But for instance, this is not equal to 2 to the power 5. So this operation is not commutative. This will be significant. Multiplication on the set of real valued 2 by 2 matrices. Again, this is a binary operation which is not commutative. Or an abstract example here, composition on the set of all functions from complex numbers to complex numbers, right? You have the elements here are functions, they are not numbers, and the operation is composition.